this is alternating currents. And the first thing that you have to look at is two coils kept very close to each other. Coil 1 and 2, of course. And the first coil carries a current, I1. There is no current flowing through coil 2. Now, surely when the current flows through coil 1, it's going to set up a magnetic field around it. And since coil 2 is very close, that magnetic field is going to be associated with coil 2, correct? And therefore, surely EMF would be induced in coil 2. Before we get to that, let's find out the magnetic flux linked with 2 due to 1. That's what that stands for. Flux linked with 2, or flux associated with 2 due to a current flowing through 1. That's how you read that. There are so many symbols coming up. Now this one would be the total flux associated with coil 2 due to the current flowing in 1. And you know that we got to multiply with the number of turns in coil 2, isn't it? So that's why you have N2 phi 21, which is the total flux associated with coil 2. And we're trying to get an equation for this one. Now, what would it depend on? Would it depend on the distance between the two coils? Certainly. Would it depend on the number of coils in one? You can talk because it can be recorded. That's okay. Now, the constant that you find there, we'll find the answers. The constant that you find there is called the mutual inductance. M21 means the mutual inductance of coil 2 with respect to 1. That is a constant which depends on the position of the coils and the number of turns in the coils, the area, and all that stuff. This is an important equation because we know that flux depends on the current, isn't it? So on the left-hand side, the total flux associated with coil 2 depends on the current flowing through 1 and that constant which is called mutual inductance. Okay? And then by Faraday's law, we know E is minus d phi by dt. So if you plug in that into this, you're surely going to get M21 di1 by dt. Why? Because M21 is a constant, right? You need not differentiate that. Are you with me? And therefore you will have di1 by dt. That is by using that equation. And that is a very important equation there. Now, if you write this the other way around, let's suppose that there was a current flowing through N2, coil 2. Wouldn't the same thing happen with coil 1? Just switch. Imagine that a current is flowing through coil 2, and then there's going to be an induced EMF in coil 1. But from your logic, can you tell me, will the constants be the same or different when you switch? Is the same two coils, the same number of turns, the same distance, everything the same? Will the constants between the coils be the same? Will their mutual inductance be the same, is my question. Yes. The answer is yes. So next time when we write it, we're going to label it M12, but it doesn't matter because M21 is exactly the same as M12. So I don't want to spend time on that. The next thing is this arrangement where you have a solenoid with a winding on top of that. Can you see that? There is a solenoid which has N1 turns, and there's another coil wound over it which has smaller number of turns, N2. So this is called a solenoid with a secondary winding. And we're trying to find out the mutual inductance of this arrangement. Okay. Let's start out with defining B. For a solenoid, we know that the magnetic flux density on the axis is given by this formula, right? We do know this. Don't we? Where N should be N1 in this case, actually. I'm going to change it. N should be N1. I1 is the current flowing. L is the length. Okay, we know that. So how do you find phi 21? Go ahead. Because if you simply sit there and write, you're going to sleep. That's being recorded too. Okay, so phi. From B, how do you get to phi? Oh, look at those faces. Multiply by the area of cross section. Correct, that's the next step. So phi 2,1, which is the flux linked with 2, due to a current flowing in 1. That's how you read it, right? Flux linked with 2 due to a current flowing in 1 is equal to B times the area. Area of which one? The area of which one? According to this diagram, they look slightly different, but consider that they are the same. So that means the secondary winding is right on top of the solenoid, okay? So their areas are the same. So it is mu naught n I1 times A. Just multiply with the area, that's it. But from the last discussion, you know N2 phi 2,1 is M12 or M21 I1. Remember that formula? We just finished that. And if you rearrange that to make phi 2,1 the subject, this is what you get. From that equation, isn't this what you get if you rearrange? Now you have two equations, and their left-hand sides are the same. So can you put the right-hand sides together and tell me what you get for M12? Please do it. The left-hand sides are the same, so put these two equal to each other, cancel out, whatever cancels out, and you get the final relation before I can show it to you. And what do you get? Whatever way you did it, you should have got this. Can I see your hands if you got it? All right, okay. So that means in this case, the mutual inductance depends on what? Depends on the number of turns of both, as you can see. And it depends on the area, which I said is the same. What's this? The length of what? Of the solenoid. Keep that in mind, of the solenoid. So that really doesn't depend on the length of the secondary winding. No, it only depends on the length of the solenoid. Third part is what is called self-inductance. Self-inductance, I would have to explain something of this, but when it's being recorded, it will not be seen. That's okay. Self-inductance, just to make you understand that, if you have a circuit like this, and just a coil here, when the switch is closed, the current begins to grow from 0 to a maximum. We've already talked about that, right? And as the current grows, is the magnetic field changing? Yes, it is changing. And a changing magnetic field always induces an EMF which is opposite to whatever is producing it. So in this case, the induced EMF is going to fight the battery. Is that right? That's called self-inductance. Because now you see that you don't have two circuits. You only have one. That's why it's called self-inductance. And wouldn't the same thing happen when you switch off? When you switch off, the current begins to decay, right, from the maximum value to 0, and again the magnetic field collapses. Induced EMF is produced, which tries to sustain the current now. You see that? When the current tries to grow, it tries to go against the growth, slowing it down. When the current decays, it tries to go against that, trying to sustain it. Are you with me? That is called self-inductance. Now to get an equation for that, now you know why it's only N phi B? Because there's no N1 and N2. It's just the number of turns is equal to, now the constant is called L there. That's not M, that's the symbol for self-inductance. Okay. Or simply stated, that is called inductance. Sometimes the word self-inductance is not used. So if you ever see the word inductance, then you know it's self-inductance. How do I get that formula? Explain that to me. Oh, will the flux depend on the current? Yeah. That's why left-hand side, the total flux is equal to a constant multiplied by current. Simple to understand that. So make inductance the subject, you get this. That's one of the formulas for self-inductance. And then we are trying to use this to find the inductance of a solenoid. Okay. We start with that formula. We know that phi is B times A. And then we know that B for a solenoid is, that's the second time we're using it, right? B for a solenoid is mu naught Ni by its length. Now, there are two, be careful about this. There's a caps L and a small l. And I've seen students cancel it out. The little one is the length. The caps one is self-inductance. If you cancel it out, that'll be the biggest mistake you ever make in your life. Okay, so now rearrange that equation, and you get the formula for self-inductance of a solenoid. That's the formula for self-inductance of a solenoid. What is in the core of the solenoid? What do you have? You have that coil, right? What is it wound on in all these equations? Actually you have nothing. It's just air, free space. That's why you have, what's this? Mu naught. What does mu naught stand for? Permeability of free space. So what if you have the solenoid wound on iron? That formula is going to change. In that case, you're going to multiply this with what is called mu r, which is relative permeability of that material, which is just showing you how many times it has a permeability greater than that of free space or air. Is that clear enough? So be careful when you have iron or when you have another material, you are going to have this formula as mu naught times mu r times n squared a by the length. So write it that way and then say mu r for air is, hello, what's mu r for air? 1. Next topic is, you are going to compare this with energy of a capacitor, energy of an inductor. Same type of thinking, but I just want you to listen very carefully to this. When you have a capacitor and you charge it using a battery, you have to do work, isn't it? And we know that the work done becomes its potential energy, electrostatic energy. What was the formula? 1/2 CV squared. Somebody said it, thank you. On the same note, the formula for energy of an inductor is going to be 1/2 Li squared. You see the constants are switched. Instead of capacitance, you're going to get inductance. And instead of voltage, you're going to get current. Because what's the process? Just try to understand what is going on. Let's say you have a coil and you have a battery connected, you switch on. This is the most important thing you have to understand. When you switch on, the current begins to increase, right? And the magnetic field increases. And the changing magnetic field induces an EMF which is opposing what the battery is trying to do. Now that's the thing that's called inductance. So the battery is having to fight against that induced EMF to set up a current. Are you with me? And work is done. Finally, when that current is set up, the inductor is capable of now storing energy in the form of a magnetic field. Because by the time the current becomes a maximum, can't you visualize a magnetic field around the coils? Now, compare this with a capacitor. What happens after a capacitor gets charged? Doesn't it store energy? But in what form? Is it a magnetic field or is it an electric field? There's the difference. So, a capacitor stores energy in the form of an electric field because, one plate gets positive, the other gets negative, there's an electric field. The difference here is an inductor. So I'm going to call it an inductor. So now you have 3. Resistance, capacitance, inductance. I'm sure you understood this. Finally, in this chapter, we're going to combine all the three together. And then you're going to get the most important circuit of all. That will be the last part of this chapter. Okay? So, how do you find out the work done to charge, to set up a current? What is the idea that you're going to use? You're finding work. What is work?
Force times distance.
That's in mechanics, force times distance, but in electricity, we know power is EI, don't we? Oh, power is E times I. And power is nothing but work over time. Therefore, work over time is EI. So what's work? Work is EIT. Simple. That's the idea we're going to use to find the total work required. Just watch. So the initial current is 0. We're trying to find the work done to set up that current. Again, as I've written, work is P dt, which is IE dt. I'm just using dt instead of t, that's all. But we know E is L di by dt. Didn't we get this formula before? Yeah, from Faraday's law. Substitute into that. When you substitute for E there, substitute for this E, what happens? Will the dt's get cancelled, please? Yes? Because you have L di by dt, and then you will be left with Li di. So to find the total work done, you integrate from the limits 0 to I. Integrate. What is the integral of Li di? Take the constants out. What is the constant? And then you have I di, just like x dx, and integral x dx is x squared by 2. That's it. So you have half Li squared. So the potential energy of an inductance is simply 1/2 times L. Well, I put I naught here to show that that's the maximum current. Okay? Maximum current. Now let's put these two together. An inductance and a capacitance together. But is there any energy in the circuit if you just put an inductance and a capacitance together? No. They're like passive devices. You know, there are two types of devices, passive and active devices. Resistors, inductors, and capacitances are passive devices because they cannot give you energy, right? A battery is an active device. But what if we had pre-charged the capacitor? So you have already charged the capacitor, and now you've connected to an inductance. What's going to happen? Before you see the math, tell me what's going to happen. You have a capacitor that's already completely charged, and you connect it to a coil. The symbol for an inductance is this one. The symbol for a resistance is this. And the symbol for a capacitance, you know, the line should have the same length. Okay? So we are assuming that an inductance has no resistance, which is practically nonsense. If you understood what I was trying to say. Because every coil should have, but for the time being, we are considering an ideal inductor. Is that clear? That means it has no resistance. It only has an inductance. Same thing with capacitance. Whenever we studied that, every capacitor will also have a resistance, but we never considered that. Remember that? Okay, that's coming in time, and we're going to consider it. Back to this. So you have a pre-charged capacitor. It's connected, and we know that the voltage across a capacitor is Q by C. I hope you know that. Okay? And you also know, we're going to set up what's called the EMF's equation, Kirchhoff's voltage law. Still remember that? So if you add the voltages across both of them, you must get? That's what we're going to do. And what's the voltage across the inductance? L di by dt. We wrote that just a few minutes back. L di by dt. Why the minus sign? Because it's a back EMF. Isn't it opposing? Okay. That's the math that's beginning out now. That's Kirchhoff's voltage law just applied. There's more than what you see there. Somebody tell me this. When you just connect the capacitor to the coil, What can you say about di by dt? Use the words maximum, minimum. Think practically. You have a completely charged capacitor, you just connected to a coil. What's the capacitor going to do? Discharge. And now my question is it going to discharge at the fastest at that instant? Or is it going to discharge at the slowest at that instant? Is it going to be fast and then get slower? Or is it going to be slow and then get faster? This is actually a common sense question. Thanks. So remember that di by dt is changing. That's what I'm trying to say. Initially, di by dt is maximum. And then finally, after the capacitor is completely discharged, what's di by dt? Zero. Did you get it? But it's not going to stop. I'll show you the math later on. Do you think it's going to stop? No. Hold on. Listen to me. The capacitor had energy, right? Now it's gone, completely gone. It's discharged. What happened to that energy now? All of it became magnetic energy across the inductance. And remember, there are no dissipating forces in the circuit, no resistance. So energy is not going to be lost at all. So what's going to happen? It's like a pendulum now. Remember the pendulum, you pull it to one side, all of it is potential energy. Let it go. What's going to happen? As it reaches here, it's going to change into kinetic energy. Do you think it's going to stop there? No. That's called mechanical inertia. The same thing happens here. It's called electrical inertia. So now what's going to happen is, as the magnetic field around the inductance collapses, it's going to recharge the capacitor in the opposite direction. What do I mean? So if this plate was positive, this was negative, now it's going to get charged the other way around. Are you seeing this? And then after the whole magnetic field in the inductance coil collapses, the capacitor's back to maximum charge and the process continues. Now let me ask you, can you see an oscillation here? It's called an electrical oscillation. Just comparable to the mechanical oscillation there. Doesn't a mechanical oscillator have a frequency? Surely, if so, an electrical oscillator also has a frequency. Remember that no radio, no television, nothing would have worked if we never had an electrical oscillator. So that's a primary function. And now the math. We're going to get an equation, but we don't like this equation. You know why? Because there are two variables there. What are the variables? What are the variables in this equation? Okay, that way there are three. Because time is always varying, I did not consider that. There are three. Q is changing, isn't it? di by dt as a whole is changing. That's why I said two. Okay. We don't like that. We want to put one in terms of the other. But what's I? Isn't I dq by dt? Hello? I is dq by dt. So what is di by dt? It's going to be d squared q by dt squared. Okay. And also I did another thing. I divided throughout by what? Somebody tell me. Divided throughout by? Okay. To get a differential equation, which you have studied, haven't you? This is called a second order differential equation. Why second order? Because it's d squared q. What's the variable now? What's the variable in that equation? Q. So what are we going to get? We're going to get q as a function of time. Are you with me? We're going to see how the charge on the capacitor changes with time. This second order differential equation has a solution. Well, I'm giving the reasons why I substituted all that. And the solution of this can be taken as Q is Q naught cos omega t plus phi. It's just assumed. Be with me. What's Q naught? Maximum charge that we started out with. Omega. Already you know, omega is the angular frequency. Didn't I talk about oscillations? Omega is the angular frequency. And phi is called the initial phase. We did waves, we know that, okay? Now, you go differentiate this, put it back into that. Go ahead. I'll give you time. Find dq by dt. I'm not doing that. So when you differentiate that twice and substitute, this is what you get. I think I wrote the whole thing, so you can check with what you wrote down. It's not a big deal. I just have to be careful. And then, yeah, I'm saying you're substituting and all that. Take out the common factor. Right? So now you have a product equal to 0. If a product is equal to 0, one of these terms has to be 0. Now, help me out. Can this term be 0? If you say no, you got to explain why. Shouldn't there be a Q naught? Yes, there must be a Q naught. I missed the Q naught. Thank you so much. Write a Q naught here, please. Q naught. It's not going to affect me because, that term, can Q naught cos omega t plus phi be equal to 0? Can it be equal to 0? What did we start with? We said Q is Q naught cos omega t plus phi. And if you set this equal to 0, then you're saying you started out with a capacitor that had no charge. Did we really start with a capacitor like that? So that means this term cannot be 0. So what's the next option? Okay, the other term is 0. And again, remember to put the Q naught, but it's not going to affect me or affect us. You know why? Because if that term is 0, rearrange. Omega is 1 by root LC. F is 1 by 2 pi root LC. Never forget this equation. You're going to use this several times in your life. If we get these oscillator to be connected to an antenna, you know what's going to happen? Those electromagnetic waves are going to go out into space. There lies radio and television broadcasting. And did you know that every radio station or a TV station has a particular frequency that they have to use? Haven't you even heard when they say, broadcasting at 88.1 megahertz? Haven't you heard that? Every time you tune a radio or a channel on television, didn't you know that you're tuning into a particular frequency? Like ABC 13, they can only use a particular frequency. Now, look at this again. Doesn't this also mean that if you could change one of them, you could change the frequency? That's what you do when you tune your radio manually. How many of you know what I'm talking about? When you turn that, actually you're changing the capacitance. It's easier to change the capacitance. Why is it easier to change the capacitance? Because remember, you could have a gang capacitor. So many capacitors together, one set of plates fixed, the other set of plates moving in and out. This is the knob that you're turning. You see that? So what you're actually doing is, you're increasing the area. You see that? The overlapping area, that changes the capacitance. That's what you're doing when you turn. And then your radio gets tuned to a particular frequency and you get that station that's broadcasting at that frequency. So we're getting into all that. Okay. LC oscillations, that's what I talked about, but I'm trying to include something now. What do you see included? So far we were talking about oscillations without a resistance, right? But coming to the practical side, every coil has a resistance. A capacitance also contributes a little bit of resistance. So in practice, what's going to happen is the same thing. What happens if you pull a pendulum to one side, let it oscillate? Do you think it'll keep oscillating until next day in the morning? No, the oscillations will die down because of dissipative forces, which in that case is the friction at the support and air resistance, isn't it? Same thing here. In this case, the oscillations will die down. The amplitude will keep decreasing. But in waves, you know there are 3 types of damping. Anybody remembers? This is damping in electricity. Damping is just reduced oscillations. I mean the amplitude decreasing. And you studied there are 3 cases of damping. Underdamped, overdamped, and critically damped. Not damned, damped. Okay, let's go to that. Let's get that equation down. Now, that is the equation that we start with. What's the new term? I times R. Because that's the EMF's equation, isn't it? That's the equation for voltage. Come on. The voltage across the capacitance is Q by C. The voltage across the inductance is back EMF. That's why it's minus, right? And what about the resistance? Isn't that also opposing? Mm-hmm. So the only real source here is the pre-charged capacitor. Are you with me? The other 2 are just, I don't like it. So now you got to substitute each one and let that roll. Same thing that we did. The new term is coming in. Rearrange all this. I is dq by dt. That's why. And I'm saying this is comparable to this equation that you studied at the beginning of the semester. Waves. Do you remember this? The answer is no. Do you see the three types of oscillations here? Can you tell me which one is over-damped? C, under-damped. A, critically damped. B. Those are the three conditions in an electrical circuit if this condition is satisfied. If R squared is less than 4 times L by C, it's under-damped. If it's equal, it's critically damped. And if it's greater, it is over-damped. That's how you know. Is there some logic in this? Yes, there is. Because look at this. Over-damped. Aren't you saying that the resistance is really high now? Yeah. What's this? You're saying the resistance is greater. Now, to get to why we got 4L by C and all that, I'll have to do the whole equation like I did the last one, which I'm not doing. And I'm sure you're happy. Because that process would take another 20 minutes, we will not finish the chapter. But otherwise, we could have done it. We could have solved it, and you would have exactly known this. My question, due to damping, does the frequency change? No, wait. What was the frequency without damping? What was the symbol? F or omega, isn't it? What do you see now? Omega prime. That means due to damping, the frequency changes. What's going to be the new frequency? That one. Again, you see the term repeated, R squared by 4L squared. So that's the new damping. Finally, if there is no resistance, what happens to this term? You go back to square root 1 by LC. That should make perfect sense. And let me also bring in a little bit more math. What if this term, the second term, I should actually be touching here. What about if this term is greater than this? Oh, come on now. What about if the negative term is greater than the first term? It's under a square root. That's when you go into complex numbers. That's when you say it's imaginary. Have you heard about that in math? It's imaginary. Which of these three cases is that one? Which of these three cases is that one when it becomes imaginary? That means it's not oscillating. Wait, what became imaginary? Omega became imaginary, right? What is omega? Angular frequency. If that's imaginary, that means there's no frequency. That means it's not oscillating. Which one of these three cases is that one? When it's not oscillating. Overdamped. That's because this term, resistance term, became greater. All right, second part. What about if these two are equal? Exactly equal. What happens? 0. Again, there's no oscillation, but it's not imaginary. Which case is that? Critical damping. And what about this case where this term is bigger, so that means this is negligible. That is where you have under damping. Man, this should all make so much sense. To the next part. The last part of this chapter, we're going to look at AC circuits and how each one behaves individually. What are the three that we have? The resistance or the resistor, the capacitor, and the inductor, right? We're going to apply an AC generator across each one and look at how they behave. That's key. That's the last part. First, the resistance. Well, that's easy to understand. If you apply an alternating current, and you know alternating current is given by I is I naught cos omega t or I naught sin omega t, right? Either one of them. So let's assume this, because your textbook takes it that way. Tell me, what would be the voltage across the resistance? What's the primary formula to find the voltage across a resistor? Yeah, use that, you will find the voltage. Use that, find the voltage. Ohm's law. So what would be the voltage? It would be, just substitute for I, you get that. Yeah. So what would be the peak value of the voltage from that? If you're paying attention, what's the peak value of the voltage? It's I naught times R, yeah. So V naught is I naught times R, and you started out with a cos function, you ended up with a cos function. So what do you know? Are they in phase with each other? Are they rising and falling together? Yes. That's the important thing. That's the important thing. For a resistance, the voltage and current are in phase with each other, as you can see on this diagram. When the voltage reaches the peak, exactly at the same time the current reaches the peak, whether it's positive or negative, maximas are reached together. That's what I'm talking about. Easy to understand. Now let's look at what happens if you do this to an inductor. We start out with the same, but remember that for an inductor, V minus L di by dt should be 0. Where did I get that equation from? We've used that a couple of times now. V is the voltage applied, and what's L di by dt? Is the back EMF. So according to Kirchhoff's voltage law, and I'm sure you understood the negative sign. So rearrange that. Make L di by dt the subject. Remember, I is always taken as I naught cos omega t. So differentiate that with respect to time. You will get. Nobody has a question on that, right? Differential of cos is negative sign. And you have to write omega one more time. Are we all together? Okay. So no problem there. Now look at this. Take a look at that. Man, the expression for voltage is a sine function. The expression for current is a cos function. So that means they are not in phase. Are they? What's the phase difference between a cos function and a sine function? Quick. 90 degrees. Oh, you didn't say that. You said something else. Anyway, it's fine. 90 degrees. But the problem is, which one is leading? When you say the phase difference is 90 degrees, you don't know which one is ahead, correct? So we're going to find out which one is ahead. Is it the voltage or is it the current? Watch. Sine theta is minus cos 90 plus theta in those math classes. And therefore, I can write in place of sine omega t, which is sine theta, I can substitute and put it in this form. Why did I have to do that? So I can compare now the current and the voltage, both are cos functions. You see this? And now it makes it very clear which one is ahead. Is it the voltage or the current? Voltage. Because in the voltage function, you have cos 90 plus omega t. That's the most important thing. So whenever you apply an AC to an inductor, the voltage across the inductance is going to lead the current by 90 degrees or pi by 2 radians. That's important, but there's also another important factor. Somebody look at this carefully and tell me, what would this be? What would this whole thing be? Maximum voltage. So now we know the maximum voltage is like crazy. It's like omega times the inductance times I naught, isn't it? Okay. That's the second thing. Watch this new term. This X stands for reactance. So you have resistance and you have reactance. Why do we call them differently? Because resistance does not depend on frequency. Resistance is the same at 50 hertz, or 60 hertz, or 1000 hertz. You see that? But a reactance depends on frequency. You see that this term is in place of resistance. Do you see that? Oh, right? But we have to call it reactance. And this is called inductive reactance. That's what the L stands for. X shows reactance and L there shows inductive. So what happens to the reactance as the frequency increases? See, one person answered. Nobody heard. What happens to the reactance of a coil when the frequency applied increases? It increases. Okay, wait. What's the frequency of DC? What's the frequency of direct current? Is direct current oscillating? Is it changing? So what's its frequency? Thank you. So if you apply direct voltages across an inductance, it has no fight. It says, go through. Why? Because omega is. But as the frequency increases, XL keeps increasing. Two things, again I'm repeating, two important things. First of all, the voltage across an inductance leads the current by 90 degrees. Second one, the voltage depends on something called inductive reactance, which again depends on the frequency. Higher the frequency, bigger the inductive. If you inductive reactance, XL, okay, capacitance, start out with I is dq by dt, isn't it? And that I is I naught cos omega t. So from there you should be able to get an expression for dq. I naught cos omega t dt, therefore q is integral dq, 0 to t. Now you're taking the integral of that. I naught is constant, take it out. What's the integral of cos omega t? Sine omega t by omega, isn't it? Okay. So you're going to have I naught by omega because of what I told you just now. So that's the voltage. The voltage across the capacitance is Q by C, isn't it? And we got the value for Q. Q is I naught by omega. So plug that in. Good. That's the end. What are we looking for? I mean, the strangest thing is when you have reached where you want to reach and you don't realize that you have reached. What are we looking for? We're looking for the voltage, isn't it? Now, what do you see again? Again, we started out saying current is a cos function. What did you end up with? A sine function. That means again the voltage and current are out of phase. How many degrees? 90 degrees. But we need to find out which one is leading. All right, this time sine theta can be written as cos 90 minus theta. So, now that's a trick, you could have written the other way too. So result number one, which one is leading? For the voltage, you got something minus 90. So that means the voltage is now behind. The current is leading. Exactly the opposite of the other one, isn't it? Okay, result number two. Somebody give me the formula for capacitive reactance. XC. What is XC? 1 over omega C, isn't it? Hello? Because according to Ohm's law, you got to have this in place of resistance. Somebody listen. Voltage is current multiplied by resistance, isn't it? So this whole thing is what? Capacitive reactance. Okay. So when you take a look at that, you understand that that's a completely different behavior. Because now you know that XC is 1 by omega C, and therefore as the frequency increases, what happens to XC? Decreases. And therefore, if the frequency is 0, what's XC? Infinite. Oh, so if you take a DC source and connect it to a capacitor, do you expect a current to flow? Perfect. A capacitor is called a DC blocker. You know what a block means? Stop. The math is right here in front of you. If F is 0, that's DC, isn't it? F is 0, what's XC? Infinite. That means it hates it. It says, no, you can't go through. So, whenever you do not want DC to flow in an electrical circuit, what do? Let's say there are so many branches and you do not want DC to go through a particular branch. What do? Include a capacitor. The best practical thing that I can think of is this. In your speaker systems, would you like to hear a hum all the time? As the music is playing, would you like to hear in the background? That is caused by DC, if there is a hum. So what do? You have a capacitor right before you take it to the speaker. What does the capacitor do? It blocks the DC and lets the AC go through. That's why it's called a bypass capacitor. It bypasses the AC and blocks the... There, you got it. Then you listen to music. If it blocks both, then you don't hear anything. That's just one of the functions that I gave you. A capacitor, an inductor, and a resistance are so useful. Look at this graph now. Before we let this go and I give you a break, look at this. Which one is leading? Which one is leading? You don't know. What we're going to see is what happens if you put all the three babies together. The inductance, the capacitance, and the resistance. But how could you combine them? You could combine them both in series as well as in parallel, right? But be thankful, we are only looking at which circuit? All right, so all three with an AC source. Oh, with an AC source across them. The current is again represented by I is I naught cos omega t. That's what we've been doing. The voltage across the resistance. Wait, why is it VRO? The maximum voltage across the resistance is I naught times R, because I naught is the maximum. According to your text, is I naught. Across the inductance, the maximum voltage would be I naught times XL. And across the capacitance, it would be I naught times okay. I naught times XC. That makes sense, doesn't it? The voltage. By Ohm's law, voltage is current multiplied by resistance or reactance. But there are three ways to go about this, and I'm using the easiest way. And this is what I'm using. What do we know about the phase differences? About the resistance, we know that the current and the voltage are in phase. Okay. And about the inductance, we know the voltage is leading the current, isn't it? Capacitance, the voltage is lagging. Now in physics, the positive x-axis represents the vector, which is the standard. So if you have the current flowing through the resistance taken along the positive x-axis, how would you represent the voltage? Same. Aren't they in phase with each other? But when you go to the voltage across the inductance, you would have to rotate the vector through 90 degrees in the positive direction. Which direction is this for you? Clockwise or counterclockwise? For you. Counterclockwise is always taken as positive in physics. So, if this is the current through all three of them, hold on. What do you know about the currents when you have components connected in series? They are the same. The currents flowing through them are the same. So the currents through all three of them will be along the positive x-axis. That's what I'm saying. What about the voltage across the resistance? The same. What about the voltage across the inductance? 90 degrees in the positive direction. What about the voltage across the capacitance? Help me out. 90 degrees in the clockwise direction. Did you see this dance? Then you understood everything. If you did, you understood everything, because I'm going to bring that up in 1 second. Voltage is generally given by cos omega t plus phi. Okay, I will have to bring this out together because the diagram came at the very end. That's why. So that's the circuit that you see. Again, I have to use this, the resistance, the capacitance, and the inductance connected to, do you know what the symbol stands for? AC source. It's actually a sine curve. You know, that's not so clear there, but that's an AC source. And the current is flowing this way. Now it says there, that's the voltage source. Those are the three components. Look at the signs, symbols, I mean, resistance, inductance, capacitance. You see all that? And what's important here is, why did I find the resultant voltage this way? Who can explain that? Why did I find the resultant voltage this way? Now that's not on this, so I'll have to draw it. Didn't I tell you? Voltage across the resistance, right? What about the voltage across the inductance? And voltage across the capacitance. How would you find the resultant of these three vectors? And I just assumed that this is smaller in magnitude than this one. You can see that, right?
Yeah.
Okay, how do you find the resultant of these three vectors? First, you would have to find the resultant of these two. That's so easy. How? One minus the other. So when you subtract it and take the resultant, aren't you going to get this minus this? Wouldn't you get something which is this small, maybe? Right? And how much would that be? Wouldn't that be VL minus VC? Hello. Let me finish this. VL minus VC, correct? And then you have to take the resultant of these two, don't you? How do you take the resultant of these two? Correct. So wouldn't that give you what I've written? Wouldn't that be square root, this one, come on,
Yes.
would be VR squared plus VL minus VC whole squared. And also when you consider that this is the square of that term, it doesn't matter if VC was bigger than, it doesn't matter. Why? But the most interesting thing is, what if both of them were equal? What if the voltage across the inductance is exactly equal to the voltage across the capacitance? Isn't that possible? Okay, if that takes place, then you know the resultant is just the voltage across the resistance. Because the other two cancel themselves out. And when would that happen? Because just now we said IXL is equal to IXC. Isn't that what we said? Because that's the voltage across the inductance. That's the voltage across the capacitance. You set them equal to each other. Plug in the numbers for this. I mean the values. XL is omega times. This is, you know, the I cancels out. This is 1 by omega C, isn't it? And you will go back to 1 by root LC. Can you see it there? Yes. Look at it. Omega squared, if you bring it up, take the square root, which is what we got before. So the oscillation frequency will be the same. And what do I mean by phi here? Which angle is phi? Surely this angle here, right? Phi, tan phi would be this, which is XL minus XC, or VL minus VC divided by this. Okay. I'm hoping I had written all that here. No. Okay, so let me give. What do you mean by resonance? Just in layman's language, if imagine I don't know any physics, how would you tell me? What's resonance? Maximum. You use the word maximum. In mechanical resonance, you are listening for maximum amplitude, isn't it? Of sound. Here, you're looking for maximum current. So electrical resonance is when you have maximum current. When could you have maximum current? Is it when the resistance is the smallest, or is it when the resistance is the biggest? Smallest. But we also have a problem here now. It's not simply resistance, it's a combination of resistance and reactance that's going to come up, isn't it? So you're going to come up with a term called impedance. The English word impede means to resist. Same thing. And impedance is represented by Z. And impedance is just square root. You will recognize this. We talked about it. R squared plus XL minus XC whole square. If you did not recognize this, you've been sleeping in the class. Because it's the same thing as voltage. All you got to do is to change from voltage to impedance. You just got to multiply. Is this making sense? And the currents are the same. Why? Because they're connected in? Yes. So the formulas will look alike. With that, let me come to resonance. In resonance, what happens to these two? They're equal. Can you see that there? And so it happens at a particular frequency when they both become equal. And if that happens, the impedance becomes just equal to what? The resistance. Would you say that the impedance is the smallest in that case or the biggest? Because normally impedance has two factors. Can you see that? You add them. And at a particular frequency, this became 0. So surely you understand that's the smallest value of impedance. If the impedance is the smallest, then the current is the biggest. If impedance takes on the smallest value, then the current becomes maximum. So I gave you the resonant frequency right now. And I'll write it out again. We know that IRMS is VRMS by this. This is what I've been trying to explain. And that denominator that you find there is what's called the impedance. This is, the whole thing is the impedance. If XL is equal to XC, then Z is minimum. That means IRMS is maximum. Everything that I told you. And that happens at this frequency. And I just called it omega naught to show that that is resonant frequency. Well, that's what we use for radio television tuning, which we discussed before, right? If you change the capacitance, you can change that. And I wanted you to look at this circuit. Before that, I want to ask you something. You've been so patient and listening. Come on. Does the resonant frequency depend on the value of the resistance? Again, does the resonant frequency depend on the value of the resistance? No, because resonant frequency is just dependent on capacitance and inductance, isn't it? So now you're thinking, what? So wouldn't there be any change if we change the resistance? Yes. Look at these three curves. Watch carefully. All these three have the same values of inductance and capacitance. How do I know? It's actually 3 circuits. What do you have on the x-axis? Omega. And on the y-axis? Current. And you have 3 different circuits. The only difference in the 3 circuits is that the value of resistance is different in each. One has 3.5 ohms, the other has 5, the other has 10. How do I know that the values of capacitance and inductance are the same? Because do you see that the current becomes maximum every time at the same frequency? Do you see this? Hello? See, do you see that the resonant frequency is 10 to the power 7, which they calculated using some values? Don't worry about that. But do you also see what happens if the resistance increases? In your radio, which one would you like to be the radio tuning circuit for you? The 3.5, the 5, or the 10 ohm? Why? Because it's a sharper curve. What does that mean? Because if you have that, you listen to only that radio station which broadcasts at that frequency, and for the others, because the curve is steeper, you cut it off faster. But if it's this flat curve, then you listen to multiple radio stations together. How would that look like? Because there's not big difference between them. You know? If you're trying to understand, you see that? You would hear one a little bit clearer, and the other one you would hear along with it, and then like 4 stations together. Oh, that would be fine, isn't it? So the best resonance curve would be the resonance curve that is the sharpest. In fact, there are 2 terms that you've got to read about. It's called the quality factor and the sharpness of resonance. Lack of time. So read those 2. Sharpness of resonance and the quality factor depends on the value of resistance. To summarize, the frequency at which resonance takes place does not depend on the resistance. You heard that, right? But the sharpness of resonance depends on what? On the value of the resistance. Okay, again, finally summarizing, that is the resonant frequency. That is the end of this magnificent chapter. Good luck.